Hello. Hello. Okay. So we are live, and yesterday we were not able to solve the problems we were discussing. So today we'll try to implement them, and yeah, I've gone through like some concepts of your binary index tree, and yeah, another thing, we could solve this problem using segment tree as well, but I'll try to implement using binary index tree only, and if time permits we'll solve it using segment tree as well. Okay, so the logic is same, uh, like we discussed yesterday. Just a second. Okay, so the logic is same. Basically we want for a particular value, particular index, we want all the values that are before, that appeared before that index and are less than the that current value. Okay, and we will add their like count. We will add the count, and then or basically we will add their dp values and then add 1 to it, because value itself can be an increasing subsequence. So yeah, that is the main logic here. But using like sorting and searching logic was not working. We tried yesterday, so we came to a conclusion that it is supposed to be solved using BIT or segment tree, that yeah, sec tree also. So if you don't know what binary index tree is, basically it is a, let's say, special type of segment tree. Can I say that? Okay, so not a special type of segment tree, but it is a data structure which divides your array, given array, into smaller sections, and those sections are their lengths are basically in powers of 2. Okay, that is what is called binary. So for example, if you have this array, so 2 1 3 4 5 1 3, or let me write it in a vertical manner. So if we have this array 2 1 3 4 5 1 3, okay, and its index is currently what, we will start from 1. Okay, basically 0 will be padded. So I mean like we do LI, right? In DP we do n plus 1 size, so we'll do that also here. Okay, and for these index, their binary representation is in binary, let's say it will be 0 0 0 1 0 0 1 0 0 0 1 1. You have 0 1 0 0, and you have 0 1 0 1 0 1 1 0, or 0 1 1 1. So what binary index tree does is basically all the it divides the entire array into levels, different levels, and those levels are determined by the these bits basically. So if if the index contains a bit in the 0th position, in a binary, so it will be a leaf node. Okay, so let me draw it here. So it will be a leaf node. Okay, all the indexes sorry, all the indexes which have a last bit set as 1, that will be a leaf node. Okay, and for the second and for the second, if the second bit is set, then from 0, from their last section's ending point, basically they will contain the answer from the answer for that section, and here it will not contain. Okay, or maybe we can we think that is how it works, right? Yeah, we divide the sections in ones and twos. Yeah, no, this is not here. This one, this will be here also. And for example 7, we have till 7 index, right? N is 7 for us, so we have 1 and 2 3 for 3. Okay, this is kind of confusing if I do it like this. Okay, so let me draw a tree. So if we start from 0 is a dummy node, so binary tree will be like this. 1, we have 2, then we will have 3, we'll have 4, 5, 6 and 7. Okay, Sorry. Okay. Hmm. Yeah. Mm, like I was saying. Okay. Like I was saying, if it is the this position, 0th position bit is set, then it will contain only the sum of that index. If second bit is set, then it will contain two answer for two values basically. So the section length will be 2. Here also it will be 2. Here also it will be 2. And for third bit, so it will have 4 values. And here rightmost bit, okay, rightmost bit, we will check for the rightmost bit only. Yes, so this is not considered for the third set bit. Okay, so we have a tree like this. Okay. So we have a tree like this, and if we see how the binary tree, basically like segment tree, this tree is not a tree but an array, but a large array. But uh, in case of BIT, the size of that array is n only, unlike segment tree which is 4n. So we will store 2, we will store 3, and we will store 5, and we will store 7. Okay, and here in this position we will store the answer for these two. So basically 1 plus 2, so 3. This is a sum. I'm showing you the sum query. Okay, so it will be 3, and here answer till for all these values will be 2, 1, 3, 6, 4, 10. Okay, and here it will be 6. Okay, so now how do we get the sum for a range A to B, and how do we add an index value? Okay, so these two operations we will look. So basically to add between a range, so binary index tree is more like a dynamic prefix sum. Okay, so instead of calculating sum between ranges, we will calculate sum from 0 to B and subtract sum A minus 1. Okay, so yeah, because it contains sum from 0, so the working of a binary index tree is like that only. So how do we calculate in range? Okay, so if we have a function which takes I as input, so basically the answer from 0 to I, the sum from 0 to I. Okay, so what we can do is we will look at first we will add the value, the ith value itself. So for example, if we want to calculate sum 4, okay, if we want to calculate sum 4. So we will add the fourth value in the array, which is 10. Okay, okay, no, this example will not work. Let me, okay, so this will work. So if you want to add the sum of first 5 elements, so I will look at the binary index. I will keep an eye on this. Okay, so this is the binary representation of 5. Okay, so what I will do is I will add in our answer the value at 5. Okay, so let's say value I is basically 5, and after this I will update I to be I with I and minus I, and I will subtract that from I. So basically what it does is it will remove the last set, basically rightmost set bit from the number. So now I will become 4. Okay, so once it becomes 4, we will add the value of 4. So you can see we have added till 4 from 0, and also we have added 5. So that is how the query works. So we have added till 5 only. Okay, so the sum query is simple, and for adding is also very simple. So if you want to add or change or update is basically update. Okay, it is basically update. So if you want to update an index with value x, so similar to this, we will add that value to the ith index itself. Okay, because we want to let's say we want to update this index 3 to 7. Okay, we want to update this to 7. We want to update this to 7. So what will be the, or let's say we want to update 4. So let's say we want to update 4 to 10 or 4 to 12. So we have 4 to 12. Okay, so if we update 4 to 12 directly, what should happen? It will be 12, and the answer will be 15 plus 3, 18. 2, 1, 3, 6 until 18. Yes, 18. So this should be okay. So we are not updating the value, I think. We are not updating, we are not completely changing it. So basically update 4 with 12 actually means, okay, so in that sense add and update are different. Okay, so add and update are different. Add means you are only adding it, so you can change it, you can subtract it or add it. So if I say that I am adding 12 to in fourth index, I'm basically doing 12 plus 4, 16 here. Okay. So in update sense it will become, I'm updating it to 16. So yeah, so adding means adding only. Yes. But mic. Okay. Adding means adding only. Yes. So after this, simple, we will add in the position itself, which is given as 4. So we will add the value, and this will be in loop, right? Similar to this will be in loop, and for each iteration we will, this time we will update with the rightmost side. But so what it is doing is, if I'm adding this, so I have 0 1 0 0 initially, and then this will give me 4. Okay, this will give me 4, but if I add 4 to 4 it will become 8. So I'm jumping a bit, right? So it is basically like this, but not for in case of 4 only it worked, but otherwise I don't think it will work. So for example, if we want to change something in 6, let's say 12 only, so for 6 it is 1 1 0 and 0 here. So rightmost bit is this, and if we add that here, what will be the result? It will be like 1 0 1 1, so it will again 0, it will become 1, so 8. Okay, so we are updating its parent also, because you see, for 4 its parent will be 8, for 6 its parent will be 8. Okay, if there was an 8th index here, it would come in this section, right? So yeah, updating also works similar to this, but instead of subtracting we are doing we are adding. So how do we use these things to solve our problem? Okay, so you see here our number can go from 1 up to 1e9. 1e9 is not storable. Basically we cannot create an array of this size. So if we create a binary index tree with this size, it will give MLE, memory limit exceeded error. So we have to do some compression. And how do we do a compression? So what we can do is, we can change it to something like this. So the smallest number we will give that a rank 1, and the number just greater than that we will give that a rank 1 plus we will give that a rank, the last one plus 1. So basically if it is 1, we will give it a rank 1. For this one also the rank will be 1. For 2, no, yes, this will also rank will be 1. For 2 it will be 2, for 3 it will be 3, for 4 it will be 4, for 5 it will be 5, and 3 is 3. So what is actually, what are we doing? We are basically limiting the maximum number that we can have to n only. So by doing this, by making the duplicates of same rank, we are if we get something like 10 to the power 8 or 10 to the power 9, the maximum index that it can have is n only, n or n minus 1 if you are doing zero based indexing. So maximum index can be n only, so we are allowed, we can then proceed with binary index tree or even segment tree. Okay, so first we will compress the indexes and we'll compress the values, and then we will compress the values. We will compress the values and then try to solve it. So we need the count of all the possible subsequence that we can extend plus 1. So for that we will do something. Okay, let's take input n and the array. You have an array, let's take it as x only. We'll take input in x, and should we make it a generalized thing? Okay. One e5. So n can go up to 2e5 now. So 2, 1, 2, 3, 4, 5. Not everything. We will then need to manually do it. So we will take from I1 to n, we will take the input and we will then compress it. So we will have a count. Okay, we will have a count, and before that we will have a map, and this will contain all the numbers. So let's do it like this. We have a map, we take the input, we add it into the map, and after it has been added, the map will now contain the element and its count, right? So we will do this. The pair, we will change the count to its rank. Okay, now that we are done, we will change the values in the original array to its compressed value. So This is basically your compression. Okay, so this is compressed now, so we can go ahead with the calculation. So we will run a loop from 0 till n. Okay, and we can get the count of candidates from our query. Okay, so for if we have the value x at ith position in the array, then we want all the subsequents and ending at x minus 1 at least, no, at most in the already solved subproblems, as we have discussed here. Like this. So we want all the subsequents ending at j such that j is strictly less than ai. So if we do a range search by doing ai minus 1, then it should work. So we will do xi minus 1, done, and we will add it in our answer. Okay, so it should be like this. We will add it in our answer, we will mod it, and then we will update it in the tree, binary index tree. So add, basically, not update, add. We will add at ith position with cc. Okay, now to make the function. So we have a binary index tree. Okay, it is working now fully. So 1, 2, 3, 4, 5. We have binary index tree, all initialized to 0, and then we'll have a add function. We will have a query function. Okay, so query will take integer I, and we are taking I only. We have the variable I is less than equal to n. We need n. We need n here. Okay, so I is less than equal to n, I plus plus. So I should be less than or less than equal to n. I plus, not I plus plus. So it is a query, right? So we are doing I minus equal to I and minus I, and we have an answer. We are doing answer plus equal to your bit I, and we will mod it and we will return it. This is for query. And for updating is similar. We have I, the bound, and instead of subtracting, we will do I and minus I, adding the last bit, and we will do bit I plus equal to that value. X, we will mod it. Okay, so update is done. Update is done, query is done, this is done, this is done. Okay, so what is the test case? 3 2 1 3. Will it work? M was not declared. MP is declared. Segmentation fault. I'm sure from here. Must be. Okay, no. Think in querying I'm getting the fault. Maybe in adding. No. So in querying we are getting the fault. Okay. So in query let me check once. Okay, so it's in the query and add function only. I think we should start from one. We have bit 0 as 0. I don't think this will make any change or Okay, so it is searching for -1, which does not exist. So it will start from 1 only. And when we are doing the when we are querying the tree, we are taking, can we print cc and see what is happening? Okay, so query is problem xi, there is no problem with xi. Okay, they are same. Xi -1, there is no problem. So I have an answer. Let's take I, and I will go till n. No, that is the thing. I greater than. uh, 5 is the answer. 5. What if I add 4? Then what is the answer? It should be 11. It should be 11. Okay. Yeah, so the issue was that I was querying, so it should be greater than 0 instead of less than equal to 1, because in that case it will always be true, since we are subtracting, so it is going towards 0, not n. Okay, so it is greater than 0. Let's try to submit it. Maybe. Nope. 43, 62, 43, 48, 40, 50. Okay. So maybe this. Not dated. No. Less than n. Okay. This is okay. I think it's an issue with modulus. Is it an issue with modulo? So let me not do this. Okay, if I do this. Same. So compression is correct. XI is replaced with its rank. We have I going from 1 to n, then we are calculating the already calculated candidate xi minus 1. Okay, and the answer we are adding in this. We are also updating the ith value. We are also updating the ith this, and adding is 10. I less than equal to 1. One and 9 plus 7. It should be 0 initially. Because we are not building the values anyway. We want count. So it will be 0 in the beginning, and when we query for the first rank, let's go till rank. Okay, we are updating the rank, so it is rank. Problem with the problem was with this, that you are not updating the correct value in the rank. Since our binary index tree is built on ranks rather than index, I was thinking it was built on index, but it is built on ranks. Okay, yeah. Oh yes. I was that was a silly mistake. The I here, if I do I here, that will be for index, but for rank we have to since the binary our index tree is built on top of the ranks only. And since we are like limited the ranks to n, so we have then built the PIT on top of that. It's because of that. Okay, so this problem we can solve using segment tree also. So for segment tree, instead of doing this, we will do 0 to xi minus 1. Okay. So that is more verbose. BIT is very clean code. See, the query and adding code is very simple, unlike segment tree where you have to make a class and all that. Of course you can do that by simply making helper functions, but it is still a lot of code. Okay, now on to discussion. Minimal grid path. Okay, so the idea for this problem is that main idea is that no, please. Okay, so the problem is let me write a little bit. Okay, minimal grid path. Okay, so we have an example here. This I'm going to copy it, paste it. Okay, so we have this example. So we are given an n cross n grid. Okay, and every square, every cell will contain a letter, and the only path forward for us from the top left cell is to go right or go down. Okay, and in doing so we have to make a lexicographically smallest string. Okay. Okay, so the first thing that comes to mind is a basic n square solution, where you will choose this and will try to go this way or this way and see if which one is smaller. Since in this case it is A, we will go to this here, and from here we will choose again here or right or down. So we will choose this, and now when we have choice of going where we can explore both right and left, we will do a recursive call. So we will go here also, and whichever gives me the minimum string, we will consider that. Okay, so it seems very straightforward until you see the constraints. So the constraints are that n can be anything between 1 to 3000. So n square, it looks like it should be done in n square, but if you try to store the string in your DP state, okay, so the string can also go up to n length, right? So in processing that, you will do n more operations, so it will become n cube operations, so that will give TLE. That will not work. Also it will give memory limit exceed. Okay, so instead of that, instead of storing a string in DP state, we should store something else. Okay, so I think you can do it in normal way instead of trying to solve it using DP. We can solve it normally. So we start from A. We will start from A. We will start from A, and then Before that, if we try to divide this matrix in a grid-like formation, okay, see how this uh, intuition can come to your mind is that when you look at a character, at a cell, the only choice for this from here, the only choice we have to of going from here is either right or down. Okay, so similarly for this, or similarly for this guy, we have the choice of going right or down. For this guy also we have the choice of going right or down. So you see, all the elements which are in a diagonal, right, they build upon the solution of this diagonal, okay, or extend this diagonal. So basically, if we are solving from the last character, then they are going to so they are building upon the previous diagonal, right? Okay, so in this diagonal, what we can do is we can store what is the best possible character that we should choose. Okay, what is the best possible character that we can choose? So how to do that? Or we can start from, so basically we need to solve in diagonals. Okay, so since the string's length will also be the total number of diagonals only, so both are there, both of them are same. So if you have n cross n grid, so the string that we need to create is of size 2n minus 2. Okay, and the number of diagonals is 1 2 3 4 5 6 7. It is 2n minus 1. Okay, so string length is 1 2 3 4 5 6. Okay, so string length is 1 less than that. Okay, so we will explore from what is the answer for this? 3 4 7. String length is also 7, na? String length is also 7. So we need to process all the diagonal elements diagonally. Okay, so for that, what we can do is we will group all the diagonal elements, and whichever one is the smallest, we'll try to reach that. Okay, we'll try to reach that. So we can do a BFS type of traversal. So we will have initially we will have A in our set. No, not A. Initially we will have this element in our set. So maybe 0 0. Okay, so we will pop it, and in this diagonal we will see which all elements are accessible, and also which forms the lexicographically smallest string. till that diagonal. So we see that we can go right. We have two options: we can go right or we can go down. So if we go right, then okay, so if we go right or down, we are going to the diagonal only, right? So we can have track of a character, of a minimum character. Okay, and if we don't, if we do not find a, okay, if we find a single minimum element, so that is where we should go, I think. So it is kind of like a greedy approach. So let's try to run it. Okay, so where is the container? Okay, so we have, this is our container. We have 0 0 at first. Okay, we pop this out. We check if we can get a minimum character by going in right, and it seems that we can. We are getting 0 1, so we will have it in consideration. Okay, we will process this and all. We will add it into our temporary storage. Okay, we will process the down element as well. We see that this thing is not a minimum character, so we will not process that. We will discard it, and we will, in the last, we will change this with we will change this with our temporary storage, or basically yeah, we'll update it with our temporary storage. Also we will add the character in the answer. Okay, in last. Now we will pop this out and see where can we go. We can go 0 2 or 1 1. Okay, so this or this. So 0 2 is C, 0 1 is A, so this will be discarded. We'll continue on with A. Again 1 1 will be put here. Answer will be, we will add answer the character. So our answer is currently A and A. Now from 1 1 we will again pop this. We have 1 1, we can go to either 1 2 right or 2 1 left, down. Okay, both of these characters are B, both are B, so both are B. Okay, so we will add both, so we will go here also, we will go here also. We will go here also. We have now from B we can go Okay, so from B we can go A, B or C. So basically from 2 1 and 1 2 we can, from 2 1 we can go 2 2 or 3 1, and from 1 2 we can go 2 2 or 2 3. No, sorry, 0 0 1 3. We can go 1 3. So 2 2 or, so which one is the lowest? So this guy is the minimum character, so we will discard this. Also okay, that is the thing. If we have double characters, same position, same B, no. So I think so I think we should see which one is giving me the minimum, and based on that we'll do it, I think. Okay, so the thing is it may give wrong answer. Okay. Okay. So if we have two choices, right? B going to be this or B this. So we will store both, and we will see which one is the minimum, and then we will keep this, and we will discard all other. Okay. And now that we have kept this, we will add this in our answer, and from there we will go. We will only have some going right. So yeah, this is how it should work. When in the implementation, I think it will be more clear, and I'm not sure if that will work also, because it is a greedy solution and it may very well fail. So yeah, let's see. Hope it doesn't fail. Don't need this. Do we need n? We need n, but just I'll have it local. We have n, need the grid. So vector of string grid n, and we'll do this. Okay, input done, and we will have a set. We will have a string answer, not there, not here. So we will have a string. This string will contain a pair of integer. I will change it to, what should we name it? Current. Okay, so in current we will have a string. Initially it will have the character 0 at 00 location, because they are starting from there, so it will always be in the answer. And we will add this to our set. So 0 0. Now we will run loop for all the diagonals. So it has 2 into n minus 1. Okay, 2 into n minus 1 is 2 into n from 1. 2 into n minus 1 I plus plus. Why we are doing this? Because 2 into n minus 1 is the total size of the string, and this loop will contain only 2 into n minus 2, and from here we will have the last one. So 2n minus 1 is the total length. Okay. And we also already processed the first diagonal from here. This diagonal we already processed, so we are doing the calculation for the next diagonals, remaining diagonals. So we have this. We will also have a temporary storage. We will also have a mini character z and c plus 1. Okay, so since we have capital English letters only, okay, a and z, so z plus 1 will be something else, I don't know. Okay, so for all the positions in our in our current, I will extract R and C detail This is basically the row and column number, and this. So here we will have two choices. If we can go right, or if we can go left. Okay, so if we can go right, then in that case we can have the right character, and we'll check if mini is less than this character. Oh, sorry. If this character is less than mini, in that case we will store this character to mini. Similarly here also we will do that. This time r c plus 1. Okay, and if ch is less than mini, then we'll do mini is equal to ch. Now that we have found the minimum, so this loop, this loop, so whatever happens here, okay, so the thing is, between these 2 points, this point and here this point, we are calculating all the diagonal elements only. So our main goal is to find the minimum in that diagonal. Okay, and those diagonals are only elements which are reachable from the last previously solved diagonals. So our aim is to find the minimum so that the string is lexicographically smaller. Okay, so whenever we whenever we find a minimum character, we will invalidate, or basically we will update the temp to contain this only, so that in the next iteration we can update the current to temp. Okay, and we will start from the minimum character. We will start reversing from that there. What I'm saying is, here we will first clear it and then we'll insert it. So now this is now the minimum in the diagonal. Okay, similarly we will do this and we will do this. Okay, minimum in diagonal. And what if the character is, if we have two duplicate characters, and what in that case? So if ch is double equal to mini, what should we do? Simply we'll just insert it. So that is also a viable path for us, so we'll insert this. Okay, ch is double equal to mini. So temp dot insert rc plus 1, and after all this we have solved for okay. So after this we will add in our answer the minimum character, and also we will set current to temp, and we'll see out answer. Let's see if it works. Okay, 0 0. Standard vector larger than max size. Wow. That's uh, okay. I'm seeing it for the first time, actually. Standard vector larger than max size. Where is this error coming from? Standard vector larger than max size. The grid is okay. Grid is 4 size. We are taking input here. 0 0 is also here. This is only for iteration sake, so no grid accessing from using I or anything. So position from current we have extracted. RNC. Maybe the issue is with this. So I'll store a character vector with T and I'll insert the first character here. Then in consecutive iterations I'll do this. And then for auto C in T, answer plus equal to C. VC is not declared. Okay. So why was it acting up? I don't know. Standard size is greater than. Weird. So let's try to submit it and see. I'm sure it will give wrong answers for most. Okay, TLE. Why TLE? Should not give TLE. So maximum that we can have is n square log n. Okay. I think in clearing and inserting again and again it is giving error. Or basically the operations are more that it can handle. So we have 2n, so 2 into 3000, and at most the total number of elements in the set can be at any time is 4. I mean n. So that is 3000. So 2 into 3000 is 3000. So basically 9 into 10 to the power 6 into 2. So 10 to the power 7, 8 into 1.8 into 10 to the power 7. And on top of that we are clearing and inserting and the auto update that the auto arrangement that happens inside the set. Okay, so it is giving daily. If you don't do it log n, then what? Okay, instead of set, can we do unordered set? What about this? Should work, right? Okay, there is hash problem. So I'll do unordered map only. Okay, let's see. Unordered map, and there not be any collision also, because keys will be different. RC, so keys will be different. Clearing and okay, let's see. So we have this, we have and do this. Temp R plus on C. Temp R plus 1. SC. Similarly, temp R is C plus 1, and here also copy paste, copy paste. Okay, so current temp current, so we'll do this here. Current 0 is 0 and current is unordered map PII, sorry, int current. Oh my god. TLE, MLE. Same thing. Okay, no. No, yes, no. It didn't work. So, clearing it is an issue. So instead of doing that, we need to do Redix sort something, so that the sorting is in log, instead of n log n, it is in it is in constant time because we have, okay, so what we can do is we will have a vector. So vector, it is current vector of size 27, and but the issue is that if all the elements and diagonals are same, then we have to include the index for that, right? Indexes for that. So we need to so we don't want this. We want we will have another vector pii. Okay, so we will have two vectors, and similarly here, so vv pi. Do we have that vector vi? No. So we will have that here, vector pii temp, and the size is similar 27, and initially all of them are null, so there is nothing there. Okay, so I don't want to clear it. I don't want to clear it. And for auto or for vector pi, v in current, if v dot size is greater than 0, then we will break here, because we want the first the minimum in the diagonal, right? So we'll break from there, and if size is greater than 0, in that case we need to give chance to all those elements. No. What we were doing was we were storing with, not with character, but with indexes, right? We were storing indexes in the current and next. So, but we were size is greater than 0. Okay, so answer will include that. Okay, so mini will be this plus the index, and so it will be okay, so j is less than current dot size, j plus 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 j. And now that we found mini, we can go and iterate all the other. Okay, so we can go and iterate the no. Okay, so there can be two options, right? If I'm here, no, if I get two characters with same if I get two characters with same basically two grid with same characters, so I'll add that to my current temp, so they will be added to temp, and I'll explore their neighbors, so this and this, and after exploring them, basically I will select the minimum. After exploring them, basically I will select the minimum. I will select the minimum. not like this. We'll do like this. For char c, from a to c less than equal to z c plus plus, if we have vc minus a dot size greater than 0, so we will terminate after that, and all the we will give them equal opportunity. Okay, so maybe I'll add them in temp. So for auto p in our vc minus a, I will take r and the column, and again I will check if r plus 1 is less than n. I will check if c plus 1 is less than n. We already have mini. I mean, that is the minimum character, right? So we have the minimum character. So we will do temp char ch is grid r plus 1 c, and temp ch dot pushback r plus 1 c. Similarly, char ch is equal to grid r c plus 1 temp ch dot pushback r c plus 1. Okay, so this is done. This is done. This is done. So our temp is populated at this point, and we can go ahead and also we have the minimum. So at the end of the slope we will update with c answer, or maybe t dot pushback c, and it is done. After this, so this is done, minimum character is done, and out of these character we will do this. We will update our current with temp. Okay, think, and it's the same thing. Okay, v was not declared, so it is not v, maybe it is c. Current, okay, it is current. Current 0 is 0. No, current 0 is this. No, We don't need to. What happened? Do you need many? No. We don't need many. So we're going from C to Z, C A to Z. Okay. Okay. Also, okay, we forgot to update. So current and okay, so this is the thing. So this is the thing. So we will do it later. So I'll just add a to it. Okay, so current 0, so it will go from 0 dot pushback 0 0. Okay, so are we getting RNC here? C. No. So we are not even getting here. No. Okay. One character. So we have that one character in our current right now, and what is the size of current? Okay, not that is an issue. So the current will hold the currently exploring diagonal elements. Okay, so from that you will get the minimum like this. We will get the minimum and add that to our answer and break from it. Why is it not working? Why? So what is the, let's see, what is the size of temporary after the first diagonal iteration? Okay, so it is 0. Yes. Yes. AAA BSEA. Let's try to submit it and see. I don't think maybe it will still give me. Maybe this time it will give wrong answers. Who knows? See? How did it get A from here? I'm setting current to temp in each iteration. This should not happen. Okay, so it looks like we were not able to solve this question today. Okay, so there is a time limit okay, so there is a issue of TLE from here and there. Also, again, why am I getting TLE? Okay, get the, I mean, I think it is because of this assignment, so it is copying, but they should be included in overall time complexity now. Maybe it is because of, no, so it is 26 and this is like what, it is n, so 26 into n, and this is 2 into 3000, so 3000 into 3000 into 52, so 9 into 52 into 10 to the power 6. So 5 into 10 to the power 8. Oh yeah, so it may give TLE. Again, how do I optimize this? Has anyone solved this problem? Good. cses solution. Okay, let's try to solve this last trap using BFS. BFS. So I'm going to remove all this also. Okay, so let me have a queue of this pair integer, and yeah, this only, and while not q dot empty, we'll run, we will push tpb in grid 0 0, we will put 0 0 in the queue also. Here I'll int size is equal to q dot size, and for, and also I'll have a minimum, mini is equal to that z plus 1. Okay, so for int I or int k is equal to 0, k less than size, k plus plus, I will pop so auto or piip is equal to q dot front q dot pop. Okay, and int r is equal to p dot first, c is equal to p dot second, and we will check if r plus 1 is less than n, or if r plus 1 c plus 1 is less than. Although we'll also have a local queue, so this is also the same. I'm going to call it local. Okay, so if the character, okay, we'll have a character ch grid r plus 1 c, if mini is if ch is less than mini, then in that case we'll update mini with ch, and we will not okay, we will clear the local. We will clear local, and we will push, I will insert, but this clearing this might take n, big of n. So what to do? I wanted to discard okay, so I'm sure it is going to go TLE. Anyway, so else if ch is mini, will insert this basically, copy this, paste this, change it a little, okay, this is done. Okay, and now we have the local, so we'll update the answer or a.pp mini, and the queue will become local, and let's see. Okay, local dot push push. Clearing queue. Okay. Why is this? Why am I getting this? 7. I should only be getting 7 and and t dot size is less than 2 into n minus 1. Okay, let's see. Submit. I'm sure it is going to give wrong answers. Oh fuck, bro. TLE runtime error. Memory limit, maybe. Okay, I tried everything. This was it. We will maybe we will try to solve it using Redux sort someday. But that was the last problem of cses, and I wanted to complete the section, DP section, today, but maybe Monday it will be finished, I think. And then we'll start solving the atcoder DP problems that are still no, we haven't solved them, like subtree problem and all, so we will do that. They are actually very hard problems, so you need to know specific concepts to solve them. So yeah, yes, that was it from my side. Like 2-hour stream. Okay, so maybe we'll see, we'll have a stream again maybe tomorrow, Saturday, right? No, I don't think tomorrow will be possible. Sunday, Sundays I usually take a day off. Okay, so on Monday only we will have a stream on Monday. Till then, enjoy your weekend, and